This is lesson 38, guys. We're doing a fundamental counting principle and permutations. Guys, we're going to start off by talking about how many different ways, guys, can you arrange A, B, and C?
Not many.
So there are a few different ways that if you had 3 different letters, maybe those little blocks you guys used as kids, and I said rearrange these letters, keep rearranging them, and give me every single different way that you can rearrange them. Obviously, the easiest one you guys would probably first off do would be
A, B, C, C.
A, B, C, right?
B, A, C. C.
Okay. Then I'm hearing B, A, C. Okay.
C, A, B.
C, A, B.
B, C, A. Oh, I'm confused now.
B, C, A.
B, A.
You can use the letters more than once, but you can't rewrite A, B, C.
C, B, A.
C what?
C, B, A.
C, B, A. There's no D. What's that? A,
C, B, A, C.
C, B.
I think
Any others?
I think that's it. There should only be 6.
Okay.
I say 1 through 2.
Yeah, I said A, C.
So, guys, this is all the combinations. How many are there?
6.
There were 6 of them. Now, remember a couple lessons ago we did things with factorials?
No.
It's because of this lesson. Guys, each one of these guys is called a permutation. And guys, all the arrangements use the same letters, but the order of those letters is different. This is a permutation, and it's just an arrangement of objects in a specific order. This is the power, guys, of having multiple things. So if I want to do a lineup in sports, and there's 3 people that have to go in a row, well then, I have 6 different ways that I can line up those people for that sport or that event. If there was a 4th person, there would even be more. But what does it seem to be? How does this work? Well, if I only have 3 things I want to use, or put 3 things in a row, I like to make 3 boxes, because I'm going to use it 3 different times. The first letter I need to put down. How many choices do I get for that first letter?
6.
No. How many letters do I have? 3. Right now, we're assuming I can't reuse them, so I got 3 choices for that first letter. But as soon as I choose one of them, the second letter, can I reuse it?
Yeah.
No.
No.
We're not using A twice in a row, or any time, we only use it once. So when I go to pick my second letter, how many letters do I have? 2. And that leaves me with only how many left? 1. And what's 3 times 2 times 1? 6. So this is why we did factorial, because this ends up being 3 factorial, or 3 times 2 times 1, which is equal to 6. So if I had 4 people, or 4 letters, A, B, C, D, the answer would be 4 factorial, which is 24. It's pretty easy, right? Now, if you look on the bottom here, it says, wait a minute, what if repetition was allowed? So now, if I go down here, it says now my number of options is going to grow quite a bit. Because when I go pick my first letter, how many choices do I get? 3. And so I write the letter down and throw it back in the hat. I go reach back into that hat. How many choices do I still get to pick from? 3. I do it again. How many choices for the 3rd time? 3. Which ends up being 3 times 3 times 3, which is 27. So if I'm able to reuse the letters or not, it makes a huge difference. Pretty easy though, right? So we just did the bottom one. Hey, if we can use them more than once, then any of the 3 letters can be used first, second, and 3rd. And that's what we showed. Any questions to that? Okay, so now now we're actually going to talk about this fundamental counting principle. Hey guys, basically this says that if I have so many choices or ways to pick the first thing, and I make that choice, and I go to make another choice using a different group of things, so I'm making two choices, using one that has A amount of choices, and the second one has B amount of choices, then the different permutations or choices that I'll have in an order of A, B is going to be A times B. Okay, what does it mean? Okay, this morning, guys, we're going to assume that you're going to put pants on this morning, okay? I know some people wear skirts, okay? But let's just say you have choices for school pants. I think there's only like 2 color choices. There's navy,
No, there are.
and there is tan.
Khaki.
Khaki's a style, not a color, not necessarily. Okay, guys, pants, guys, and then we're going to go with school shirts. We're going to go with the polos, not the other stuff. So, how many choices of colors of pants do you have? 2. How many shirt style colors do we have? 3. We have white, blue, and green. So, in this particular fashion, with just the different choices of pants, and then choosing a shirt color, we have how many different styles or choices? We have 6 different combinations. See, you guys are all different. You guys can all wear your different clothes. It's awesome. Think of this now. We start adding different pieces to that. The number of choices and styles you guys can have starts to get larger and larger, right? But that's what it means. You take the amount of choices from each one independently and you multiply them together. Wait a minute. I think most of us, if not all of us, have eaten at a Subway shop. Whether it's Subway or one of the other ones. You have about, okay, I know Subway. Think of this. Subway has about what? How many choices for bread?
6.
Like 6, okay? So there are 6 choices for bread. How many different meats, we'll say?
Oh, like 5.
I would, there's at least 10, okay, right? There's chicken, there's turkey, there's the meatball, there's the, all those different things. So, conservatively, guys, conservatively, can I say there are 10 choices for the type of meat you want? How many different types of cheeses are there? 5 or 6?
I'm just making these up.
I don't know. There's about, what's conservative here? 5 types of cheese. How many different vegetables can we put on there? If we're just putting one vegetable. About 7?
You can only put 1 vegetable.
We're just going to assume 1 vegetable. If you want to put 3 vegetables on, then you just have the choices that many times. Okay, very conservatively, making a very simple sub, choosing a bread, a meat, a cheese, and 1 vegetable. 4 things. Multiply all those out. How many different sub combinations can you have? 350. So 60 times 5, which is 300 times 7. 2,100 different sub combinations. Now, like Drew said, what, you only put 1 vegetable on? What if I wanted 5 different vegetables?
Yeah.
So now you have to multiply that 5 times. Then you're starting to get even larger combinations. Guys, you ever figure out why someone doesn't win the Powerball every time? Because you got 1 to 60, you got to pick 1 ball out of 60 5 times or something like that. So that means it's like 60 choices times 60 choices times 60 choices times 60 times 60. That's a large number.
Check what it is.
You get a 1 in that chance to make that happen. So, let's start doing this ourselves. How many different ways, because these are the type of problems you're going to see in your homework, how many different ways can the numbers 3, 5, 7, and 8 be arranged if no repetition is allowed? We're assuming we're using them all. So how many are there? There are 4. So how many boxes am I going to make? 4 boxes. 3 down lines there, because that makes 4 boxes. Now, how many choices do I get for the first box? Well, how come it's not 8? It's 4, but why is it not 8?
Because there's 4 numbers.
Because 8's a number. That's not how many numbers I have. So be careful on that. Yes, there are only 4 choices. Once I establish that I'm putting a number down, how many do I get for the second one? Or third one? 3, and then 2, 1, which ends up being, I think we said this earlier, 24. You have 24 different number combinations. Hey, even a sidebar on this one. Most of us, or a lot of us, have an Apple device. And if I wanted to go to a very, very simple, I heard that today you can actually make it harder. The simple basic codes would be how many numbers? 4 numbers.
You can make it to 6 numbers.
Someone said up to 12. I don't know which that's for. Okay. Okay. Listen. So we got 4 choices. I'm going to put this on the bottom here. You have 4 choices, or 4 numbers. How many choices for the first one? 1 through 9 and 0. So there's actually 10. Can I reuse those numbers in this process? Yeah, so repetition is allowed. So that means there's 10 here, 10 here, and 10 here. How many different codes with just 4 numbers? It's not 40. We're multiplying.
10,000.
It's 10,000. Can you think of why the FBI wants Apple to break into their device? Because they got a 1 in 10,000 chance to getting it right.
Well, I mean,
If it's a simple code. Okay? So, statistically, you can probably pick which ones are used more, like 1, 1, 1, 1. But little things like that, or 1, 2, 3, 4, which you shouldn't use ever. But this is the power, guys. If we add 1 more number, all of a sudden it goes to 100,000 codes. It's mind-boggling how this works. It's pretty cool. Okay, last problem on this slide. How many 4-letter signs can be made from the letters of the word equal if repetition is permitted? Wait, how many letters am I using? No. Oh, I'm using 5 letters, sorry. How many am I using at a time? 4. I'm making a 4-letter sign. That's what I was looking for, sorry. I'm using 4 letters at a time, but I get to choose 5 of them. So, again, how many boxes then? 4 boxes. So I'm only getting to choose 4-letter signs. These 4-letter signs might make gibberish, right? Because I'm going to use the letters. How many letters do I get to use in the first spot, though?
1.
How many letters are in equal? 5. Can I reuse that letter, though? Yes. So how many do I get to check for the second one? 5. And 5 again, and 5 again, because I keep on reusing letters, if I can. So, 5 times 5 times 5 times 5 is 25 times 25. 625. There are 625 signs that can be created using those 5 letters. 4-letter signs. So again, some of them aren't going to make sense because you'll have something like Q-E-A-L. I don't know if that's even a word. But it can be a sign. It doesn't have to be, anything that's perfect. Any questions, guys? It's all about how many letters are you taking, how many you can use, stuff like that. Now, this one's an interesting one. We're going to take a test today. And that test has 8 questions. Each question has 4 multiple choice possibilities. How many different answer sheets can we create? So would there be enough that everyone in here could create their own answer sheet? Someone might put A. Someone might put B. Someone might put A, B, C, D, right? Those are all different scorecards. We only have 8 questions with 4 choices. So how many different possibilities are there?
Can we try that and see if anyone does the same one?
Okay. So, we got to think of this. How many boxes do I need? There's 8 questions. So how many boxes? So this is like my sine. Each of these questions has how many choices? 4. Guys, this is actually the fundamental counting principle problem. And each one has 4 choices. So each of these choices get multiplied together. Now, someone right now is probably going 4 times 4 times 4 times 4 times 4.
The 8th power.
Do 4 to the 8th power. Guys, it's the same base, and they all have a power of 1. And so if I add up all of those, I had 8 of them, it becomes 4 to the 8th power. I think that's a little easier to put on my calculator. What do you get? How much? I think that was 65, I thought it was. 65,036. There would be 65,000, over 65,000 different combinations of scorecards. That's crazy. Think of your ACT, guys. There's 4 or 5 choices. I'm not sure, I don't remember anymore. So, let's just say the math portion has 4 questions still. How many questions are there? There's 60 of them. That's an astronomical number of different scorecards that you could possibly have. And there's only one right one, right? Next one, how many 3-letter signs can be made from the word numeral if no repetition is allowed? So how many letters are we going to end up taking?
3.
Only taking 3. How many get to go in the first box?
1.
I'm pulling the letters from numeral. There are 7 choices. How many do I get to go for my second letter? 6. Why? Because I can't repeat. Once I've used it, I got to throw it out or leave it on the sign. And then the third one is?
5.
So it's 7 times 6 times 5 and you're done. Okay? I'll let you guys handle that. Any questions to that? Okay. Now, this is an interesting one. You guys have done this before. It's called designated roots. Guys, roots are solutions. So, can you guys solve that equation I have on the board? And every one of you guys better be able to say yes. What do you do with those? No, that's not. That's putting it back together. It's already factored. Set each equal to 0. And then add 3, so x equals 3. Subtract 5, so x equals -5, right? So those are the solutions. I'm going to call those the roots. Roots or solutions. What we're going to do today is not factor it to solve it. We're going to be given this, write them as this, so that we can write this, so we can multiply it or FOIL it together to get our quadratic back. We're going to go in the reverse direction. So these are called roots, and we're going to go in the reverse order. Now remember, all of our problems are going to tell you it has a leading coefficient of 1. So in front of x squared is going to be a 1. 2, all rational and complex solutions always come in pairs. Why? Because when you're solving for x and you take a square root, what always is there? Plus and minus. And when you have complex solutions, as in I, you always have its partner negative I. You get those because we're square rooting again. Okay? Any questions to this? So here are your steps. Going in that opposite direction. I'm going to take the solution and I'm going to set it equal to x. I'm then going to bring everything to one side or set it equal to 0. So now I have x minus 2 equals 0 or x plus 3 equals 0. Those are now factors, guys. Those are those things that we first started off with on that original problem we did. And all I need to do then to get my quadratic back is to multiply them together. Write the quadratic equation with a leading coefficient of 1 whose roots are -3/5 and 1/2. So set them equal to x, right? How do I get those equal to 0? It says that right above. Bring everything to the same side as the variable. So what do I need to get rid of 3/5 by doing? Adding 3/5. So I'm going to add 3/5. So that means this is x plus 3/5 equals 0. If I subtract 1/2, x minus 1/2 equals 0. Right? That's nothing big. The last step says multiply those two things together. Why we do this is because this and these two pieces here are those factors from the other slide that we set equal to 0 to solve. And so now it's just x plus 3/5 times x minus 1/2. Still equals 0, guys. Because if one number or both numbers equal 0, when you multiply it, it equals 0. How do you multiply those together? FOIL it. Not a big deal. You guys can handle FOIL it. Make sure you get a common denominator to put things together, because we do have fractions in this problem. What you have to worry about on the problem below is, look at this. Now, I've got that square root thing. Now, rational numbers, square roots, this has a positive one and a negative one. These are partners already. How do I bring these all to one side? Subtract 1 and subtract the square root of 2. The other one is still subtract 1, but this one is add square root of 2. Does everybody see that? And I have to do that to both sides. So what do I get? I get x minus 1 minus the square root of 2. Then I get x minus 1 plus the square root of 2. And then I just have to do what with those two? Multiply them together. Wait a minute, Mr. Contract, you just said FOIL on the last problem is what you have to do. This is FOILing, but it's an extension, right? Take the x, distribute, take the negative 1, distribute, and the square root of 2, distribute. You guys have all done those things before. What will happen here, though, your square roots will disappear. You will not have them. And remember, we're building quadratics, so the highest power should be 2. Overall average rate. Guys, if we're taking a trip in a car, we know the distance equals rate times time. We should also know that the rate is the distance divided by time. And we should also know that time is the distance divided by rate. All things we've been talking about for several of our lessons. But we're going to focus on the overall average rate. Average means add it all up and divide by the total, right? That's what average rate is. It's the total distance divided by the total time. That makes sense. If I was taking a trip from here to Florida, I don't know, I have it on the board over there. I said, hey, what if that was 1,000 miles? And I completed that trip in 22 hours. That's miles per hour then. If I take my calculator out, it's 45.45 miles per hour. Does that mean I strictly stuck to 45 miles per hour from the time I jumped in my car to the time I stopped? No. That means sometimes I was probably going faster than that. Sometimes I was going slower than that. Sometimes I wasn't moving at all because I was at a restaurant eating, right? But it's my total distance divided by my total time. Does that make sense? So our problems here, guys, are just going to ask you questions like Frank and Judy. They go for one leg of their trip 100 miles at 50 miles per hour. They then drive 100 miles, 180 miles at 60 miles per hour. What is their overall rate or speed? First of all, how far do they go? 100 plus 180, which is 280, right? But we have to divide that by what? Total time, right? Okay. Now, guys, we need to find something. We got total distance, but we got to divide that by total time. It doesn't tell us time. How do we figure out the time? How do we figure out the time for that first leg? Distance divided by rate. Oh, so 100 divided by 50 is 2 hours. The next leg was 180 divided by 60, which is 3 hours. So our total time of this whole entire trip was, right? It was 5 hours because I can add those together. So there's miles. That's a bad miles. Over 5 hours. Total distance divided by total time. What is 280 divided by 5? 53? 56? 56, okay. 56 miles per hour. 56 miles per hour is their overall average speed. You get a problem like that, it shouldn't be a big deal. What about Bill and Sam, though? Bill and Sam say they drive for 100 miles at 50 miles per hour. They then drive 180 miles at 60 miles per hour. Hey, wait a minute. They're copying Frank and Judy. But then it says, how fast must they drive for the last 120 miles? Oh, so they basically are going a little bit further. They're taking a third leg of their trip, aren't they? To have an overall rate of 60. So they want to go faster than Frank and Judy overall. So what do you think that means for that last leg? You think they're going slower on the last leg or faster to get an overall average speed to go faster? They would have to go faster, right? So how do I set this one up? Well, first of all, do we know the overall average? Yes, and that is what? No, it's the overall is 60. So 60 is going to equal what goes on top? Total distance. What are our distances? 100 plus 180 plus the last leg, which is 120. Now we already did this leg work. We did this leg work already here. How long did it take them to do the first leg for 100 miles? So 2 hours plus the third 3 hours for the 180. And how long does it take them? We actually don't know, do we? So can I call that x? Can you solve for x? I think so.
Could you just put the 5 hours and then put the 280 on top?
So 60 equals, what's the top number? So 400 over 5 plus x. Now you have to cross multiply.
Can you just put 5 hours on the bottom and then 280 miles on top?
No.
Why not?
Well, you could have, because that's what it adds up to. But you had to add that third trip into it. So you got to.
It would have been the third trip, but I wouldn't have added the.
It'd have to be all lumped together. You can't do them separately. So, I think we should agree that 60 times 5 plus x is equal to what? 400? How many people want to distribute the 60? I think I'd rather divide it out. Okay? Well, if we divide this out, I think we'll have 5 plus x equals 40 divided by 60. Well, I can divide the top and bottom by 10 and get rid of 0. And what's 40 divided by 6? 20 over 3?
Yeah, something like that.
Not a nice number, but now all I have to do is what? Subtract 5. I got to get a common denominator. Oh, man. Multiply bottom and top by? 3. 5 times 3 is what, guys? So what's 20 minus 15? 5 over 3. 5 over 3 what? What were you solving? X on the bottom was what? Time. And time was in hours. So we found it to be 1.6 repeat hours, or 5 divided by 3 hours. Does that answer our question? And the answer is no. Because it asks us how fast. And fast is speed. And how do I find rate? Distance divided by time. So how far? So distance divided by time is rate, right? How far do I go on that third trip? 120 divided by 5/3. I think there are going to be speed difference here, I think. How fast am I going? Are they going? Sorry. 72?
That's nothing.
So 72 miles per hour for 120 miles. On average, that's how fast they went on that last trip. To make it so that they would have a 60 miles per hour average speed. You see the two difference between these two problems? One, you can just add them all up and just divide it. Pretty simple. The next one, you have to start putting things in and realize that you didn't have a time. But that time was not the solution to the answer. So answer the question. So lesson 38, page 274, 1 through 3, 6 through 11. Have a great day.